All right, welcome back, Academic Astronomy. Good to see everybody. Happy May, and check it out, I got a haircut. Now, you might be thinking, wait a minute, Mr. Krug, you're not supposed to be out getting haircuts right now. Actually had Mrs. Krug cut my hair. So, fellas, little advice out there, have your lady friend, or I guess guy friend, it's 2020, have them learn to cut your hair. First couple times might not go too well, but then you're going to be in the clear. So if there's ever a future pandemic, you're still going to look smooth and have a nice cut while everybody else is looking nice and shaggy. So let's get started today. We are going through our last section of section 7, Stars and Galaxies. So I'm going to go through the last couple pages of notes here, and then we're going to pause to have you fill out some questions. And again, this video is not going to be locked, so you can switch back and forth between this video and the questions. And once again, if you do have a PDF of the notes, that's good. Even better if you've printed out these notes, then you can just follow right along. So good to see everybody. Let's go ahead and get started here. So let me share my screen. Okay, so here's where we left off last time. We were talking about the deaths of stars, and we learned that there's a difference between how average to low mass stars like our sun versus high mass stars like supergiants die out. And we talked all about black holes and how awesome and mysterious they are. So for our last lecture today, we are going to go through the potpourri, just the leftover pieces that we haven't covered yet for this section. And first, we're going to start out where it all began on page 1, the birthplaces of stars, nebulae, which is just the plural of nebula or nebulas. This is nebulae. So these are clouds of gas and dust. And we also learned that we can't assume that every single cloud is a leftover remnant where a star lost its life long ago. A lot of these clouds are just still present from the birth of our universe. And I only show this diagram in academic astronomy. I found it online. I think it's awesome. This comes from Sunflower Cosmos, and it shows all the different types that we have. Diffuse is a general term for a cloud of gas and dust that's giving off light, but they can do it 2 different ways. We have emission nebulae and we have reflection nebulae. So an emission nebula is one where the atoms of gas are actually so excited themselves that electrons are getting stripped off and they are giving off light. Reflection nebula is slightly different. Here, the cloud of gas and dust itself is not giving off light, but nearby stars, and sometimes even stars that were just born within that nebula, are illuminating that cloud of gas and dust. M42, the Orion Nebula, is often given as a common example of a reflection nebula. Then, when we do talk about deaths of stars, we have 2 different types here. Our average to low mass stars like our sun are going to end in what we learned are planetary nebulas. So again, it's a bit of a misnomer, actually has nothing to do with planets, but this is a cloud of gas and dust that's left when a star like our sun, but older, will poof, blow off its outer layers. Normally, a ballpark way to tell these apart from supernova remnants is a planetary nebula is more symmetrical. It's often circular in shape because this is a low energy explosion of the star peacefully blowing off its outer layers. In contrast, though, we have a kaboom of a supernova remnant that a high mass star would give off. Oftentimes, these can be asymmetrical because it's such a high energy event. So some examples that we've learned in class: M57, the Ring Nebula from Lyra the Harp in the summertime sky, would be a perfect example of a planetary nebula. Whereas M1, the Crab Nebula above the lower horn of Taurus, the Bull, is an example of a supernova remnant of a stellar explosion that the Chinese observed back around the year 1060 or 1048 AD. Finally, we also learned 1 or 2 examples of dark nebulae. So this would be a cloud of gas and dust where the light itself or the gas itself is not giving off any light, nor is any of it illuminated by nearby stars. However, the reason we can see dark nebulae is stars back behind the cloud are basically showing us the outline. So here you basically have to think about outer space three-dimensionally, even though to us on the sky, it looks relatively flat and two-dimensional. In this small picture that you see here, basically the cloud of gas and dust is closer to us. And then the star field that you see, which highlights the boundary, is actually farther away. A great example here might be the Horsehead Nebula, which we learned below the belt of Orion the Hunter, not far from M42, the Orion Nebula. Finally, for this first part on nebulae, we have lots of beautiful colors of nebulae. I think time exposure photographs of nebulae are among the most beautiful pictures of deep space ever taken. But you can also tell that they're colored a variety of ways. And over here to the side, you can see a picture of what's called the Eskimo Nebula, and you can see the great color diversity in these clouds of gas and dust. So why are they colored this way? Well, for a lot of nebulae that appear red or pink, it is because of an abundance of hydrogen, by far the most abundant gas in the universe. So usually emission nebulae are this color because of something called the Balmer lines. When electrons get excited to a certain level, as they drop off, they will basically radiate in specific wavelengths. And a lot of times it's red or pink. However, in contrast, if you see a nebula that is predominantly blue, like M42, the Orion Nebula, or maybe the Pleiades star cluster, this is likely a reflection nebula. The gas and dust is reflecting the light of the new stars around them, and usually they're young baby blue stars. Finally, if we have some miscellaneous colors like green or yellow, it's because of high energy stars like blue supergiants actually ionizing the hydrogen gas, which means it's so powerful and energetic, it is literally stripping electrons off of those atoms, and they'll appear green or yellow. Okay, this time we're going to do things slightly different than the first two sections, because did you know there's a chance some students, I know not you, but some students weren't actually watching the videos. They were just fast forwarding the whole way to the end to actually get to the questions. I know, totally shocking. So this time I'm actually going to ask the questions as we go through the videos. So all of you cool teens that are paying attention and following directions are going to have no trouble with this at all. So at this point, you can start switching back and forth between the questions in Google Classroom and this video and pause it at any time. So these questions today are going to be numbered 21 through 30, and they are the final questions for our notes packet. So here we go. Number 21. This subgroup of diffuse nebula is caused by the light of nearby stars reflecting light off of a cloud of gas and dust, making it visible. Number 21, please pause the video and answer the question. Got my Berenstain Bears big hug mug today. Fantastic. Number 22, the Horsehead Nebula, which we now know well from Orion the Hunter, is a famous example of what type of nebula? And if you forget, just do a simple Google image search for the Horsehead Nebula. Number 22. And number 23, due to their abundance of pink light, we can assume that portions of the Lagoon and Trifid nebulae, found above Sagittarius the Archer, if you recall, are this type of nebulae. Number 23. All right, let's get back to the action then with the notes. We'll pick up the rest of the questions a little bit later. So let me go ahead and share my screen with you again. Hopefully you're following along. So letter I, what are some other interactions that stars can do? Well, maybe you've noticed on your star charts throughout the year that there's a symbol on there that's a black dot with a little white hole in the middle. That's a symbol for a variable star. The root word is vary, meaning to change. So what about these stars is changing? It turns out their brightness is changing, but we're going to see that it happens in two very different ways. So the first type of variable star are called intrinsic variables. This, everybody, if you can recall that seesaw analogy I've been using throughout this section with gravity on one side of the seesaw and star energy on the other side, this would be a star whose seesaw has never stabilized. It continues to teeter-totter back and forth throughout its life. When gravity is stronger, the star gets smaller and dimmer. When star energy is more prominent, the star gets bigger and brighter. So bigger, brighter, smaller, dimmer. Bigger, brighter, smaller, dimmer. These are pulsating stars called intrinsic variables, and we'll talk more about them in just a little bit. The second type of variable star we have are eclipsing binaries. Now let's break that term down. Bi means two, and then eclipsing, there's some element of eclipsing or light blocking with these stars. So check out the diagram here because it explains it really well. This would be not one star, but at least two. This would be maybe a double star or a binary system where both stars are orbiting around each other. And when one star passes in front of the other one, that light output that we see, because for most double stars, we're far enough away that to us, it just looks like a single point of light on the sky. That single point of light will get brighter and dimmer, brighter and dimmer. For example, you might remember the star Algol, the demon star from Perseus the hero. The ancients could actually see it changing brightness, which made them think it was evil. We know now, though, Algol isn't evil. It's simply an eclipsing binary star. Now, if this light output graph looks familiar to you, this is also a very similar way to how many astronomers hunt extrasolar planets, because they can even see a very teeny tiny change to the light output of a star as a very small planet goes in front of it. But their instruments have to be incredibly precise, because I once read that trying to spot a planet eclipsing in front of another star would basically be like trying to watch a ladybug crawl across the headlight of a car from over 1 mile away. The other thing, everybody, to realize about eclipsing binaries or finding other planets this way is we actually have to be in the correct line of sight from Earth. For example, there is no up or down in outer space. So as long as a star system is oriented like this to us, we can see it. But let's say it's oriented the other way, and we actually have a bird's eye view, and we don't see this eclipsing happening. Then we wouldn't actually see this light output graph changing. So these are both types of variable stars. Now, when we have a double star system, some other things can also happen, and at least one of them is terrifying. First, let's talk about the less terrifying option. This is called a nova. Now, sometimes students confuse supernova and nova, and the easy way to remember this is a supernova is a super explosion, kaboom! Whereas a nova is just a regular explosion, like a kaboom. I sometimes like to call these star burps or star farts. So what's happening here to the left is an artist's illustration. If you have two stars too close to each other, one of them with a stronger gravitational pull can start to actually siphon gas off the other one and cannibalize it. And when it gets too much gas on it, there's a small kaboom, and just the excess gas explodes. The star temporarily gets brighter, and that is called a nova. So I call them star burps or star farts because what happens when you have too much gas in your stomach? Does your chest explode? Do you catch on fire? No. You just burp, you release that gas, and then everything is fine. So that's a nova, and unlike a supernova, it doesn't destroy the star. But, bump, 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 there is one time where this can lead to a supernova. And this, my friends, is the only time a lower mass star can actually explode. So very quickly, let's backtrack a couple pages here to our stellar evolution diagram. Here we go. So follow me down the average or low mass chain. You might remember there was one single dotted line I added from white dwarf over to supernova explosion. So this, everybody, is the one and only time that a lower mass star can actually explode. If a white dwarf is in a binary system, like let's say with a larger but far puffier red giant, and the white dwarf, as you see in this illustration, is sucking so much gas off of it, it can actually cause the core to collapse and implode. And that will lead to a kaboom called a type 1a supernova. Now, these potentially could be very dangerous. As I mentioned in the previous lecture, astronomers have looked at all the massive supergiants within 30 light years of us, and there aren't many, and none of them are going to supernova anytime soon. But the one danger is we could have a lurking binary star system out there where a white dwarf does supernova. So this is the one time that a low mass star can actually explode. Okay, the final thing we'll talk about here, and I got some beautiful illustrations for you. This is before I ask another couple questions. You might also remember from your star charts, there's a symbol of a dotted circle on them. These are star clusters. They are groupings of stars in space. Now, the reason that astronomers are so excited about these, everybody, not only are star clusters beautiful, but it basically gives us a movie of how stellar evolution is working. So instead of just getting snapshots at far different places in a star's life, astronomers know that most stars within a star cluster will be more or less the same age. So then by comparing star clusters of different ages, they can tell how these stars are evolving. And so we have two main types of star clusters. I've got some great textbook examples of both. On the left here, you see open clusters. So an open cluster has to have at least 10 stars, but definitely less than 1,000. And they're in about a 25 parsec region, which ballpark is a little over 75 light years. Now, the big difference here, not only are there less stars, but notice everybody, the stars are spread out enough that you can see the blackness of outer space right through the middle of them. A perfect example that we learned here would be M44, the beehive cluster in Cancer the Crab. On the right, and in my opinion, some of the most beautiful objects here on the sky, these are globular clusters. As the name implies, it is quite literally a glob of stars. So we could have anywhere from 100,000 up to 1,000,000 stars in a region less than 100 light years wide. So one example that we looked at would have been M13, the Hercules globular cluster in the constellation of Hercules, which you can see well during summertime. So this is a globular cluster. So just think about that. There are places out there on the sky where there are over 1,000,000 stars in a single pinpoint of light. So I think the universe must just be teeming with life. In fact, back in the 1970s, astronomers Carl Sagan and Frank Drake actually beamed a radio message from Earth at M13, the Hercules globular cluster. And their reasoning was they could basically reach about 1,000,000 star systems with this message at the same time. However, even though a lot of stars are packed together, personally, I think it's probably very unlikely that we find life around the center of a globular cluster. In here where I'm pointing right now, everybody, the stars are so close that anytime one of them pops off in supernovas, kaboom, it would sterilize all the outer space and the other star systems within 30 light years of it. So more than likely in a globular cluster, we might find life around the outer rim. Okay, you're all doing great. Let's take a break and let's ask a few questions about this page of notes right here. How do I stop sharing my screen? It's still sharing and I don't want that. Oh, found it. Stop share. All right, we're back. Okay, let's head back to the questions. Okay, question number 24. These types of stars change brightness over a period of time, although they do so in two dramatically different ways. Question number 24. Question 25. This rare type of stellar explosion is the only supernova that takes place with low mass stars. Question 25. Also got some water here. Cutting my coffee with my water. And finally, number 26. Please image search M13, a cluster that we learned during the summertime within the constellation Hercules. What type of cluster would this be? Question 26. All right, let's get back to the action here. Only about a page or so of notes to go. Hope that you're enjoying this, everybody. Okay, I've got some great stories for you about galaxies. So today we basically take for granted that our own Milky Way is one galaxy, one stellar big city, but there are many, many other galaxies out there. But how did they ever figure that out to begin with? Sometimes I think one of the disservices that we do in science is we basically just share the information with you as students that scientists have figured out over time, but we often overlook the stories on how they figured it out. And to me, that's the really, really fascinating part. So think about this. If you looked at a galaxy through a backyard telescope, like let's say M31, the Andromeda Galaxy, how would you actually know that it's a totally different place rather than just a cloud of gas and dust, like a nebula that's much closer to us? Well, for that, let's enter one of the most famous astronomers of all time, Edwin Hubble, whose name has become a household name, obviously due to the Hubble Space Telescope, which actually just celebrated its 30th anniversary in space at the time that I'm making this video. So Hubble, using very large observatories, was able to look very, very closely at these clouds of gas and dust. But even when you look at a galaxy through a large telescope, there's not like a sign there that says, hey, I'm a galaxy. So how did he actually figure this out? Hubble made two very important discoveries for which he is very famous. When we talked about variable stars and we talked about intrinsic variables, those stars that are actually pulsing bigger and smaller, one type is called a Cepheid variable. And they're called this because the first one ever discovered was in the constellation Cepheus the King, which we remember from the NCP sky. And it turns out with Cepheids that they pulse at a very regular rate, and their light output as they're pulsing is very, very consistent. So Hubble, with this huge telescope, was actually able to find Cepheids in distant galaxies. And so he looked at how much the Cepheid was dimming down, and he realized that dimming was caused by an enormous distance. And so for the very first time in history, we knew that our Milky Way was just one galaxy, but there were many, many other stellar big cities out there. Hubble wasn't done yet. Along with a colleague, he later looks at the light output given off by these distant islands in space. And he found that the light was something called redshifted, meaning as the object moved away from us, it actually stretched out its light waves like an accordion. And so Hubble does some calculations on the extreme redshifts that he was seeing. And he realized the only way these redshifts were possible is if the universe was expanding quite rapidly. And so we'll talk about that expansion just a little bit later. So what we have here, everybody, is a great diagram that I have modified ever so slightly. So because galaxies are so far away, one of the only ways that we can really tell them apart is through their shapes. So this was Edwin Hubble's classification scheme. Sometimes it's known as the tuning fork diagram because it looks like a big old tuning fork. So ellipticals are basically galaxies that have no spiral arms. They range from more circular to more elongated. Then we have spiral galaxies, and we have barred spiral. So spiral galaxies usually have a circular nucleus or nuclear bulge and multiple spiral arms. Barred spirals have a stretched out barred shaped nucleus and usually only two arms. Now, I've never seen this actually proven, but I tend to think my own personal belief is probably most galaxies begin as spiral galaxies. Then, when they have one collision, their first collision with another galaxy, they start to stretch out and they form barred spirals. A lot of supercomputer modeling of galaxy collisions shows this exact thing happening. And then, if they have at least one more collision, that can strip off all the arms, and those then become ellipticals. My reasoning here is the light of stars in most elliptical galaxies is red, meaning the stars there are a lot older. So these tend to be our older galaxies. So just my own hypothesis, what we do know is there are different galaxy shapes. Now, if it doesn't match one of those three shapes, we would just add it to this potpourri group here called irregular galaxies. Now, what might our own Milky Way be? Well, for the longest time, astronomers assumed that we were in a spiral galaxy. But we now think there's a chance our galaxy might actually be a barred spiral. And you might think to yourself, well, how in the world don't we even know what our own Milky Way is if we're inside it? That's actually the problem, everybody. We're inside our galaxy. And as humans, we can't travel fast enough or far enough to actually get out of the Milky Way, turn around, and take a look down at it. So here's a perfect example I give. Pretend that once the quarantine lifts, you are going to have a sleepover at a friend's house. You're really, really excited about that. And let's say it's a good buddy of yours, but you've never actually been to their house. And you don't get to their house until it's already late at night. But you go in and you have a really good alcohol-free teen time at this sleepover. So then the next morning, you wake up in your sleeping bag in your friend's living room. But before you get out of the sleeping bag, your friend comes over to you with a tablet of paper and a pencil and says, here, based on what my living room looks like, I want you to try to draw a picture of what you think the outside of my house looks like. You'd probably agree that that would be pretty challenging to do, only seeing your friend's living room. But it gets even tougher than that for astronomers because we're actually in the back broom closet of our Milky Way. And on top of that, there's smoke filling the entire thing. So that's why it's so tricky to figure out where we actually are. What shape our Milky Way is. Now, what we actually, or where we actually are, is a little bit more known. And I have a great diagram of that here. It turns out our sun is in the forgotten outskirts, the boondocks of our own Milky Way. And this was first discovered by an astronomer named Harlow Shapley back around World War II. Ironically, even after we figured out for certain that Earth is not at the center, that we actually orbit the sun in the heliocentric universe of Copernicus, people still naively assume that our sun had to be at the center of the Milky Way. And Shapley showed for a fact that was not true. What Shapley started to map are these globular clusters that you all see here, which we just learned about. Some globular clusters are in the plane of our Milky Way, but many orbit around the outside. And Shapley started to map them and the directions that they were moving. And he found far more globular clusters in this direction towards Scorpius and Sagittarius in the summertime than he did over here in this direction. So for the first time, we knew that not only is the Milky Way one galaxy of many, but we are way out at the edge of it, out in the boondocks. So finally, some mysteries of deep space. The first thing we're going to talk about before I ask some more questions are quasars. These are objects that even today are somewhat of a mystery to astronomers. We know they are incredibly bright. They almost look like distant bright stars, but they have a tremendous amount of mass to them. They have as much mass as an entire galaxy would have. Further, they are some of the most distant objects we can see. Some of these quasars, everybody, have been spotted about 12 billion light years away. Now, if you think about this, if our universe truly is 13.7 billion years old, and the deeper we look into space, the further and further back we see in time, that means just by seeing a quasar, we are looking back in time almost to the beginning of our universe. And so some astronomers think these quasars may have actually been the earliest galaxies, essentially the first wave of galaxies after the Big Bang. So there's a chance, even though we can see the ghost image of their light, some of these quasars are no longer there. Okay, hang in there with me. Let's ask a few more questions before we wrap up the last page of the notes. Just 2 questions this time. Number 27. This famous astronomer was the first to realize galaxies were their own separate stellar big cities and that the universe was expanding. He classified galaxies according to their shapes. Number 27. Number 28. These objects are so bright and so distant that they may be the earliest galaxies in our universe's history, some of which are no longer even there. Number 28. Okay, great job, Astro Teens. Let's finish up this final page of notes now for section number 7. So let me go ahead and share my screen with you one more time. All right. Ooh, got a good alien story for you on this one. So mystery number 2 of deep space. These are gamma ray bursts, and they are enormous explosions of gamma rays that are spread throughout deep space. They are exponentially more powerful than a supernova. In fact, if the muzzle blast of a gamma ray burst ever pointed directly at the Earth, it could actually fry the Earth from thousands of light years away. So I know that being a teenager is tough. You get frustrated with your parents, your teachers, your friends, and sometimes you think, oh my gosh, this is the worst. But honestly, anytime that you wake up and Earth is still pretty much regular and everything is okay, that is a very, very good day, because we can see that survival in the cosmos in some ways is kind of a crapshoot. So let's talk a little bit about gamma ray bursts. The leading theory is that these form from powerful jets as a supergiant actually begins to supernova. They also think it could be when the beams or the jets from a black hole are pointing in our approximate direction. There's even a suggestion that a gamma ray burst could happen when neutron stars collide. Now, were we in class, I also have an awesome article for you from Universe Today, where some astronomers even hypothesize these could be muzzle blasts from distant alien weaponry. Allow me to explain. There's a chance, however bleak this might be, if we ever discover an advanced civilization, the first message we get won't actually be a faint whispering radio signal bringing peace, but it might actually be the inadvertent outburst of a very large weapon that they are using. For example, here on the Earth, did you know the first wave of UFO sightings in the United States happened in the 1940s? Curiously, also in the 40s, we began to test the very first atomic weapons as part of the Manhattan Project. So some people actually think that due to this pop, pop, pop of these very powerful weapons going off, other civilizations, which may have known Earth was here and may have thought that we were relatively primitive, now to their shock saw the telltale signal of muzzle blasts and came to investigate. Now, you might still be pretty skeptical on this idea, and that's totally okay. But here's the one other curious thing about gamma ray bursts. It turns out that they're not spread evenly over the whole night sky. They are coming in anisotropically, which means from one preferred direction. So you would think if this was a truly natural phenomenon, over time, we would basically see them spread evenly across the sky, but we do not. They actually come from one direction. So still such a mystery, gamma ray bursts. And speaking of mysteries, everybody, these two are one of the biggest challenges that physicists and cosmologists, astronomers who study the evolution of our universe, are facing today. And that is dark matter and dark energy. So let me try to explain both and what we seem to know about them so far. Let's start with dark matter. There is a chance that up to 80% of all the universe's matter. So think about that. That would mean 4 out of every 5 atoms cannot even be seen yet. And that is this idea of dark matter. So far, astronomers have been able to detect dark matter in basically 2 places. When they look out into the deepest regions of outer space, they can tell some places the fabric of space-time has actually been bent, just like Albert Einstein predicted in his general relativity, except sometimes they can't even see the mass that's actually doing the bending. So that's one place for this hidden matter or dark matter. Another place comes in the halos surrounding galaxies, which we just talked about a bit ago. When astronomers look at how fast galaxies are rotating, they are rotating much faster than our conventional equations tell us they should be. In fact, in theory, galaxies are spinning so fast that they should basically just fling themselves apart into outer space, except that they don't. They continue to stay cohesively together. So that's another source of dark matter. In contrast to that, we have what is called dark energy. Now, in a way, this was actually inadvertently first predicted by Albert Einstein in what he considered one of the biggest mistakes of his career, but it's actually come back around and it might actually be real. So when Einstein really started to explore the implications for his general relativity, he realized that according to his equations, the universe should not be static. It should either be expanding or it should be contracting. And Einstein did not like that very much at all. Einstein, despite being a phenomenal scientist, also had a great philosophical tilt to him. And he really liked the idea of a static or an unchanging universe. And so he basically added something called the cosmological constant, this extra ad hoc variable, to try to keep it always in place. And he later realized that the universe probably was expanding and was very embarrassed about doing this. But it turns out that it might actually be true, but we would call it something different today, and that is dark energy. And it's not that the universe isn't expanding. Cosmologists are pretty sure that it is, but it seems like we do need this additional variable in play. So when we look at the rate of the universe's expansion, and astronomers look at the most distant galaxies and they see how redshifted they are, it turns out that the farther we look, the faster and faster the universe seems to be going. There is no loss of energy. And it seems like there is some additional energy that is present there that we cannot yet factor in that explains this amazing rate of expansion. And so far, that's been dubbed dark energy. So some people liken dark matter and dark energy to being opposites, opposing forces of each other. Dark matter is like the glue that tries to hold the universe together, whereas dark energy is trying to fling it apart. So we might see some major discoveries within our lifetimes along with these two things right here. We might even find that one of them isn't exactly true, at least not as we currently know it. So finally, back to Einstein, that brings us to the shape of space itself. So Einstein wanted to think that the universe is static, but his equations told him that would be highly unlikely. It would be almost like trying to balance a pen or a pencil on its point. In theory, it could balance for just a little bit, but eventually it would tip over one way or the other. So right now, cosmologists look at 3 possible shapes for the universe. If our universe were spherical, that would mean the universe is finite, only so big. And it would eventually come back together in what's called the Big Crunch. In fact, kind of cool. If our universe was really spherical, like an old school video game, you could actually shoot out one side of it and come back in on the other side. That would be like the original Mario Brothers. Not Super Mario Brothers for Nintendo, but the actual coin-op Mario Brothers where you had all the platforms and Donkey Kong up on the top. You could actually run Mario off one side of the screen and then he would come back in on the other side. Astronomers, though, think this one is unlikely because years ago they actually looked at the cosmic microwave background, basically the first echo of the blast after the Big Bang, and they looked for places where the background was repeating itself, and they could not find any, so they think a spherical universe is unlikely. Let's skip down and talk about the flat universe. This is certainly the type that Einstein would have preferred. In a flat universe, true parallel beams of light would stay parallel for an infinite length, and this would lead to a stationary universe. We tend to think this is unlikely, largely because of the pioneering work that Edwin Hubble did. And interestingly, Hubble, even though he's given credit for the universe's expansion, was still somewhat uncomfortable with that idea, just like Einstein. But because of Hubble's work, right now we lean towards the universe being negatively curved or saddle-shaped. Everything keeps getting bigger and bigger and farther apart. And in theory, this will eventually lead to the big freeze, which we talked about back in section number 1. Okay, I have talked just about long enough, so let's get to the last couple questions so you can finish up the notes. Here we go. Number 29. Opposing dark energy, this hidden presence has been detected in the halos surrounding galaxies and helps keep the universe from flying apart too rapidly. Number 29. And finally, number 30. Because cosmologists lean towards a big freeze as the fate of our universe, they also favor this shape of the universe the most. Question number 30. Okay, teens, you've been amazing. Thank you so much for sticking with me through these 3 lectures. I know they did get a little bit long. Mr. Krug talks a little bit too much, but when it comes to deep space, there are just so many amazing scientists and so many cool stories that go along with it that I just can't help myself. So make sure that you did answer questions 21 through 30 and keep a copy of these notes handy because eventually we are going to have a quiz on them. So for me, with my new haircut and my Berenstain Bears coffee mug, peace out, everybody. Have a great day.